Okay, so we are going to look at the standard normal probability table. Let's talk about what a normal distribution is first before we get started. So in chapter 5, we looked at discrete probability distributions, for example, like the number of customers. So it's not continuous. These are whole numbers. Well, now we're going to look at continuous probability distribution. So the graph's going to look like this. It's not going to stop, whereas here you go from, for example, 1, 2, 3, 4, 5, 6. It's choppy because it's only whole numbers. So continuous random variables take on any numerical value in an interval. So they're they're usually measured rather than counted. So here these are typically counted 1, 2, 3, 4, 5, 6, 7. And what we're going to look at in this section is continuous items that can be measured. So the purpose of this chapter is to identify the probability that a specified range of values will occur. A range of values will occur for continuous random variables. Okay, continuous random variables can take on any value, and because there are an infinite number of values, the probability of just one specific value is pretty much equal to 0. So if you want to know the probability that x is equal to 3 with a continuous, it's going to be super close to 0. So those will be easy to find if it asks you for the probability of just one value. In section 2, which is what we're looking at, we're going to look at normal distributions. And so let's look at what a normal. So that is going to be what we call our bell-shaped curve. If you were to draw a line down the middle, it would be symmetrical. Then we're going to look at exponential. Its graph will look like this. It'll start out high and go down very fast. And then uniform is the same over time. So a normal distribution, when to use this? This is when data tend to fall into the center of the distribution and very high and very low values are rare. We're going to be using the actual tables for this, and remember these are in the appendix. So let's look for the probability that z, okay, z, let's talk about z because we need to get a little bit more in depth before we start. So this is your normal distribution. The center of it is your mean and your median. When you have a normal distribution, your mean and your median are going to be equal. And this is a symmetrical shape. And the reason it's symmetrical is because the mean and the median are the same. So the values near the mean, this is where it's the tallest, okay? And everything under this curve is probability. So everything under this curve is going to add up to 1, your total probability, okay? Now, this area here is higher, which means it has a higher probability. But the further away from the mean you get, the probability gets smaller and the curve gets shorter. And the characteristics of a normal probability distribution, I did mention that everything under the curve is 1. And because it's symmetrical, each side is 0.5. Another thing to know about normal probability distributions, this line here is the mean. So if you increase the mean, the line's going to move to the right. If the mean is decreased, the distribution is going to move to the left. As far as standard deviations, the smaller the standard deviation, the skinnier the curve will be, and the larger the standard deviation, the wider the curve will be. So any normal distribution can be transformed into a standard normal distribution, z. So you need to transform first x units into z units, okay? And once you get the z unit or the z value, it's called a z-score. And so we have kind of talked about z-scores before. It's going to be x minus your mean divided by the standard deviation. Okay, z-scores that are negative are going to be less than the distribution mean, and z-scores that are positive are going to be greater than the distribution mean. And the z-score at the mean is going to be 0. So you are converting the mean. If it's 5, if the mean is 5, the z-score is going to be 0. So here is what happened. So say our mean was 5 and we converted it to a z-score. Now our mean is going to be 0. Okay? And when you convert the standard deviation to a z-score, it is going to be 1. Okay, here's an example. The time customers spend on the phone for a service follows the normal distribution with a mean of 12 and a standard deviation of 3. And it's asking what is the probability that the next customer will spend 14 minutes or less on the phone. So first you have to plug in and get your z-score, okay? So think about our picture here. Here's the mean. Okay, here's our value somewhere above the mean. Okay, now when we convert this to z-scores, the mean is going to become 0. So the z-score, since this value is to the right, the z-score has to be positive. If the value was to the left, the z-score would have to be negative. So here you can see that it is positive. All right, and here is the actual graph that I was talking about. You can see the mean and the x value. Now the mean becomes 0 and the z-score becomes 0.67. Okay, so if you use your table, and I'm going to show you how to do that, and you wanted to know the probability of it being less than or equal to 14, you're going to look at the table, which is going to be cumulative, but you're going to look up for a z value of 0.67. So you're going to go to your table and you're going to find 0.67 on your table, and it will give you the probability up to that point, so it's cumulative. Okay. Now, we actually, in this problem, we want to know the probability of x being greater than 14. So what we're going to do is use the complement rule and say 1 minus the other side. So our answer is 0.2514. These complement each other and add up to be 1. So that's kind of an overview of what we're going to be doing in this section. And in the next video, we're going to start working problems.